Kinematics and Vectors. Example 2. So we have a particle with this initial velocity and it has a constant acceleration. We need to work out the velocity vector for any given time. We have a SUVAT problem in vector form as we have constant acceleration and we're given vectors. So initial velocity, this is what we're after, the constant acceleration, and we want time in our formula. We're not interested in the displacement. So v equals u plus at. So u, 3i plus j, is here, plus the acceleration, 2i plus 3j, multiplied by time. And now I've grouped the I components together and the j components together, which will aid problem solving. So this vector formula will give the velocity at any given time t. Now we want to work out the bearing of the particle at t equals 3 seconds. So we start off with our velocity vector, which was this. We substitute in t equals 3 here and simplify. So now we have the velocity vector at t equals 3 seconds. To work out the bearing, we need to use some simple trigonometry. So the velocity vector along here, its components, 3i plus 10j. So tan theta is the opposite over the adjacent, so we can work out the angle theta. We're looking for the angle alpha, but we need to use bearing notation, so it's the angle clockwise from north. So alpha is 90 minus theta, so we've got the angle alpha, so the bearing is 017 degrees. Example 3. A particle has an initial velocity given here, so that's for t equals 0, and it has a velocity at t equals 20 seconds given here. Now we're given that the acceleration is constant during this time period, and we have to work out the acceleration vector. So this is a SUVAT problem using vectors. So we start off with our basic variables here. So we're not interested in the displacement. We've got initial velocity, velocity at 20 seconds, and we're after the acceleration. V is equal to u plus at, our vector SUVAT formula. We substitute our values in, and now we need to rearrange. We've got an I term on the left hand side, we have an I term on the right hand side. If I move this term to the other side, so minus 5.6i minus 2.4i, and we do something similar with the j terms. Now we've got this, and then divide by 20 throughout, and we have our acceleration vector. And this is a constant, this is a constant. You can see that the acceleration vector is a constant. It's not a function of time. None of these terms have t in them. A constant acceleration, hence the use of SUVAT formulae. Now the same problem done using column vectors will have the following working out. So this is just v equals u plus at, rearranging, simplifying, t is equal to 20, and then we can divide both of these by 20, or we can multiply by 1/20th, which does the same thing, and then this scalar quantity will multiply our vector here, so both the x and the y components are multiplied by 1/20th, and we get this. And these numbers here are exactly the same as what we have here.